Hello and welcome back. In the last video, I mentioned that if we have an expression for a curve such that when I increase the parameter by 1 unit, I also increase the length of the curve by 1 unit, that's a really special property for us to have, right? We know that for any given trajectory, if an object's following that trajectory, you can follow it a lot of different ways. You can travel at variable speeds along it and still do the same trajectory. And so if we're just studying the curve, we're going to want a way to sort of normalize this. So we're just studying the curve. We don't care at what rate it's moving along the curve, just the curve itself. This is going to allow us to study things like curvature and torsion of the curve. So that's sort of what we're working towards. And in this video, we'll be discussing how we can take a parameterization of a curve and convert it to one of these special arc length parameterizations, right, where the speed is 1 along the entire curve. So this is going to be a theoretically very helpful thing to do for us to obtain these arc length parameterizations and work with these. So let's work through an example here. Again, what we're looking for to determine if we have an arc length parameterization or not is we want to look at the speed, right? The magnitude of the derivative of of r of t. If that speed's 1, then we have an arc length parameterization, and vice versa. So that's what we want to have happen. How can we achieve that? Because just given a curve, that's not always necessarily true. We're going to have to mess with it a little bit, change the parameter. Okay, so I want to find the arc length function, and this is from t for t greater than or equal to 0. So this will be my a in the arc length function definition. So s of t is the integral from 0 to t of the magnitude of my derivative of r prime of t. And I don't want to, so the whole idea is I don't want to reuse that variable t, so I just use a dummy one. I'll call it u here, du. It's not going to matter when we integrate this. Right, because, so let's go ahead and actually find this for this curve. So r prime, what's r prime of t? R prime of t is minus 2 sine t, 2 cosine t, and then 4 here. And so I'll put, how about magnitude of r prime down here? Magnitude of r prime of t then is square root 4 sine squared t plus 4 cosine squared t plus 16. Sine squared plus cosine squared is 1, so this is just 4 plus 16. That's square root of 20, or 2 square roots of 5. So s of t is 2 square root of 5. It's the integral of 2 square root of 5 du. I'll do it like this. I'll do it longhand du. And so that's 2 square root of 5u. I just want to show you why it doesn't matter what this parameter in here is, and that you don't really need to worry about it, because then we integrate this from 0 to t, and I just get 2 square root of 5t. So that is my arc length. S is 2 square root of 5 t. So if I increase the time value, if I increment it by 1, I'm increasing the arc length by 2 square roots of 5. So that is the speed at which I'm traveling along this curve. That's my ds dt, is 2 square roots of 5. That's my rate of change of the arc length with respect to the parameter t. So if I want to get an arc length parameterization, well, I'm going to solve for t here. 1 over 2 square root of 5 s is equal to t, and I'm going to take this t and put it in for t here. I'm going to reparameterize, or rather put it in here. I'm going to reparameterize in terms of this. So that is, if I, instead of doing r of t, if I input 1 over 2 square root of 5s in for my variable, so this is my new parameter, what'll this look like? This will look like 2 cosine of s over 2 square root of 5, and then 2 sine of s over 2 square root of 5, and then, what, 4 over 2 square root of 5. So that's 2 over square root of 5s. So now this vector-valued function with this new parameter, right? It's going to be the same. All I did was change the parameter, so the trajectory is exactly the same. But now, when I increase the parameter by 1, notice it's an s here because it corresponds exactly to arc length. Now the object travels with a speed of 1 around the curve. That my parameter and the arc length are exactly matched up. And that's what we're going to want. All right, so that's sort of it for this section. This is really kind of a building to the next section type of thing, kind of giving us the frameworks that we need to talk about certain aspects of the curve, like curvature and torsion, things like this. All right, I'll see you there.